Separations of the components of a mixture. Calculation. In this video, we will discuss the calculations for the separations of the components of a mixture experiment. These demonstration calculations will be performed using data that I collected for the experiment. The calculations will involve determining the mass of each component and then calculating the percent of the total unknown mass for each component. To calculate the mass of each component, we will need to subtract a residual amount of unknown from the total unknown mass. To calculate the percent of the total for each component, we will divide the mass of each component by the total mass of the unknown and multiply by 100%. Lastly, we will compare the recovered amounts to the total unknown mass we began with. The first step is to calculate the total mass of the unknown sample that you began with. For my data, the mass of the empty evaporating dish was found to be 39.601 grams. The mass of the dish plus the unknown sample was 42.222 grams. The mass of the sample is found by subtraction, so that the mass of the sample is equal to the mass of the dish and sample minus the mass of the dish, which is equal to 42.222 grams minus 39.601 grams, giving a mass of 2.621 grams. The sample was then heated to sublimate the ammonium chloride. After the dish had cooled to room temperature, it was reweighed. For my data, the dish, after heating, had a mass of 41.829 grams. To calculate the mass of ammonium chloride in the original sample, we subtract the mass of the heated dish from the mass of the dish plus the sample. This results in a value of 42.222 grams minus 41.829 grams, or a mass of ammonium chloride equal to 0.393 grams. Next, we can determine the percentage of ammonium chloride in the unknown. The percentage is the ratio of the mass of ammonium chloride to the total mass of the sample times 100%. Thus, to calculate the percentage of ammonium chloride, we have the mass of ammonium chloride divided by the sample mass times 100%, or 0.393 grams divided by 2.621 grams times 100%, which gives a value of 15.0%. Now we can turn our attention to the sodium chloride. The mass of sodium chloride is calculated as the difference between the mass of the large evaporating dish with the watch glass and sodium chloride and the empty dish plus watch glass. For my data, the mass of the dish plus watch glass was 194.865 grams, and the mass of the dish plus the glass plus the sodium chloride was 195.857 grams. We can now calculate the mass of sodium chloride as the difference of these two values, which gives 195.857 grams minus 194.865 grams, or a mass of sodium chloride equal to 0.992 grams. As before, we can now determine the percentage of sodium chloride in the unknown. Again, this percentage is the ratio of the mass of sodium chloride to the total mass of the sample times 100%. To calculate the percentage of sodium chloride, we have the mass of sodium chloride divided by the sample mass times 100%, or 0.992 grams divided by 2.621 grams times 100%, which gives 37.8%. Now we can determine the mass of the remaining component, silicon dioxide, and this is found as the difference between the mass of the original dish with the dry silicon dioxide and the empty dish. Recall that for my data, the mass of the empty dish was 39.601 grams. The mass of the dish plus the dry silicon dioxide was measured to be 40.794 grams. Thus, the mass of the silicon dioxide can be found as the difference of these two masses, which gives 40.794 grams minus 39.601 grams, or a mass of silicon dioxide equal to 1.193 grams. Finally, the percentage of silicon dioxide in the unknown can now be determined. As before, the percentage is the ratio of the mass of silicon dioxide to the total mass of sample times 100%. So to calculate the percentage of silicon dioxide, we have the mass of silicon dioxide divided by the sample mass times 100%, or 1.193 grams divided by 2.621 grams times 100%, which gives a percentage of silicon dioxide of 45.52%. Now that the masses and percentages of all of the components have been determined, we can compare with the original mass. To do this, first we will calculate the total sum of the masses of all components, where the mass of separated components is equal to the sum of the mass of the ammonium chloride, the mass of the sodium chloride, and the mass of the silicon dioxide. This gives 0.393 grams plus 0.992 grams plus 1.193 grams, for a total mass of the separated components of 2.578 grams. Next, we will calculate the difference in the mass recovered and the original mass. This is calculated by taking the mass of the separated components that we just calculated and subtracting off the original sample mass. For my data, we get 2.578 grams of the separated components minus 2.621 grams of our original unknown, which gives a value of negative 0.043 grams. Please note that because my recovered mass was smaller than my original mass, my difference is negative. The final calculation is to determine the percent recovery for the experiment. The percent recovery is the ratio of the mass of separated components to the original sample mass times 100%. The percent recovery becomes the mass of the components divided by the mass of the original sample times 100%, or in this case, 2.578 grams of recovered components divided by 2.621 grams of the original unknown times 100%, which gives a percent recovery of 98.36%. This concludes the calculations for the separations of the components of a mixture experiment. Report guidelines and a fillable data sheet are provided on Canvas. Please be sure to show all calculations as stated in the guidelines. If you have any questions regarding the guidelines, the data sheet, or the calculations, please be sure to contact me.